There is a version of a black hole that fits neatly inside a city, and there is another version so large that if you were falling into it, you would not feel anything at all for years. These are not metaphors. These are real categories of the same object, and they are so different from each other that for decades, scientists were not certain they were even the same kind of thing. A black hole is not a hole. That is the first thing to let go of. It is a region of space where gravity has become so extreme that the escape velocity exceeds the speed of light. Nothing gets out. Not radiation, not information, not the memory that something was ever there. The boundary where this happens has a name, the event horizon. Cross it, and the universe you came from is gone forever. What remains on the other side is, by definition, unknowable. But what sits at the center is stranger still. A singularity. A point of infinite density where the laws of physics as we write them today simply stop working. The equations reach a value and then collapse into themselves like a building with no foundation. Some physicists believe singularities are real. Others believe they are a sign that our mathematics is incomplete. We do not yet know which side is right. What we do know is that black holes come in types, and the difference between them is not just size. It is origin, behavior, and in at least one case, sheer impossibility. Start with the ones that should be most familiar. Stellar black holes form when a massive star runs out of fuel. For millions of years, the star exists in a state of perfect tension. The energy from nuclear fusion pushes outward. Gravity pulls inward. The moment fusion stops, gravity wins instantly. The core collapses in less than a second. The outer layers rebound in a supernova that can briefly outshine an entire galaxy. What remains at the center is compressed beyond any prior limit. A stellar black hole typically contains between 5 and 20 times the mass of our Sun, crushed into a sphere roughly 30 kilometers across. That is smaller than most major cities: London, Tokyo, Los Angeles. A black hole the size of the urban core of any city you have ever stood in, containing the mass of 10 suns, bending space so severely that light orbits around it before falling in. Our sun will not become one. It is too small. In about 5 billion years, it will swell into a red giant, probably swallowing Earth in the process, and then collapse into a white dwarf, dense but stable. The threshold for a stellar black hole requires a star at least 8 times more massive than the Sun at birth. We got lucky with the size of our star. Or perhaps it was never luck at all, and the kind of stable, long-lived star that allows life to emerge simply cannot be the kind that ends in a black hole. The universe may have arranged it this way by elimination. But there is something stranger waiting one step further up the scale. In the centers of most large galaxies, including our own, there sit objects of almost incomprehensible mass, supermassive black holes. The one at the center of the Milky Way is called Sagittarius A star. It contains 4 million times the mass of the Sun. 4 million solar masses compressed into a region roughly the size of our inner solar system. If you removed the Sun from the center of our solar system and replaced it with Sagittarius A star, it would fit within the orbit of Mercury. Every star in the galaxy, including our own Sun, orbits around it in a slow gravitational dance that takes hundreds of millions of years to complete. And Sagittarius A star is not even large by supermassive standards. At the center of the galaxy M87, there is a black hole containing 6.5 billion solar masses. In 2019, a global network of radio telescopes called the Event Horizon Telescope captured the first direct image of this object. It appeared as a ring of orange light surrounding a dark interior. The ring is not the black hole itself. It is the photon sphere, a region where light moves in circles around the event horizon before some of it escapes toward us. The image took years of processing and the combined data of dozens of observatories on multiple continents. When the result was revealed, one of the lead scientists, Katie Booman, had written the algorithm that made it possible while she was still a graduate student. The photograph she had never expected to actually see reduced her to tears in a server room. It was the first time in human history that anyone had looked at the edge of a black hole and seen it looking back. But the origin of supermassive black holes is one of the most unsolved problems in modern cosmology. Stellar black holes form from dying stars in a process we understand reasonably well. Supermassive black holes should have taken billions of years to grow, and yet we have found supermassive black holes in the very early universe, when it was less than 1 billion years old, already containing billions of solar masses. They should not have had enough time to form. Some grew too fast. And science does not yet have a satisfying explanation. This is not the end of the list. There is a proposed middle category called intermediate black holes, objects containing somewhere between 100 and 100,000 solar masses. Not quite stellar, not quite supermassive. For a long time, they were considered theoretical. The mass range seemed to have no clear formation pathway. Then, astronomers began finding candidate objects in the centers of smaller galaxies and in dense globular clusters. In 2020, gravitational wave detectors picked up a signal from a merger that produced an object of roughly 150 solar masses, placing it squarely in the intermediate range. The existence of intermediate black holes is now considered likely, but confirmed examples remain rare enough that they are still listed as candidates rather than certainties. And then there are the ones that should not exist at all. Primordial black holes are hypothetical objects that would have formed not from dying stars, but from the extreme density fluctuations in the first fractions of a second after the Big Bang. Before stars, before galaxies, before the universe had cooled enough to form atoms. If pockets of matter became dense enough fast enough, they would have collapsed directly into black holes ranging from microscopic to millions of solar masses before a single star had ignited. No one has confirmed that primordial black holes exist, but they remain one of the strongest candidates for dark matter, the invisible substance that makes up roughly 27% of the total energy content of the universe. If the universe is filled with tiny primordial black holes too small and cold to detect, they could account for the gravitational effects that galaxies, galaxy clusters, and the large-scale structure of the cosmos cannot otherwise explain. We may be living inside a sea of ancient black holes left over from the first moment of creation, and we would have no way of knowing. There is a final category worth holding still for: the rotating black hole. All the types described above can rotate. A stellar black hole formed from a spinning star will itself spin. A supermassive black hole fed by accreting gas tends to spin at enormous rates. But a rotating black hole is structurally different from a non-rotating one. The mathematics describing it, worked out by Kerr in 1963, reveals something that should not be possible. A rotating black hole does not have a point singularity at its center. It has a ring singularity, a one-dimensional loop. And the equations suggest that inside that ring, the gravitational field does something that defies every intuition. It becomes repulsive. The mathematics even permits, at least on paper, pathways through the ring that would exit into a different region of space-time entirely. Whether these pathways are physically real or just artifacts of incomplete equations is a question that remains genuinely open. Kerr himself spent decades wrestling with what his own solution implied. Every black hole we have ever detected, every shadow we have imaged, every gravitational wave we have recorded from a collision, every star we have watched orbit an invisible mass at the galactic center, all of it points to objects that are consistent with the mathematics and yet remain fundamentally alien to direct experience. We can calculate what happens at the event horizon. We can describe the photon sphere, the ergosphere, the innermost stable circular orbit. We know the equations. What we cannot do is stand at the edge and look down. And somewhere in the universe right now, there is almost certainly a black hole that does not fit any of these categories. Something outside the mass ranges we have mapped, formed by a process we have not yet identified, behaving in ways the current models do not predict. The gravitational wave detectors have already found objects that challenge every known formation pathway. One merger produced a black hole too massive to form from a single stellar collapse and too small to be the result of previous mergers alone. Astronomers called it the impossible event. They gave it a catalog number and moved on, but the name stuck in the informal literature. What is inside the impossible event? What formed it? And if black holes this strange exist in the space between galaxies, how many more are drifting silently through the dark, too cold and too distant to ever betray their presence to anything we have built?